All right, section 4.3, trig, extended, the circular functions. When I say extended, I mean outside of quadrant 1. So when we were doing section 4.2, which was trig of acute angles, I told you we were only in quadrant 1. Well, that's because, triangles, all their angles are, less than 180 degrees, right? The three of the angles together add up to 180. So typically, a lot of your angles are going to be less than 90. But we've all seen obtuse triangles, right? So we know that some of those angles are bigger than 180. What that means, bigger than 90. What that means is that we should be able to do trig in triangles of any size and shape. So we need to be able to perform trig of obtuse angles, angles that would land our terminal ray in quadrant 2. But here's the thing. In all actuality, that ray could land in any of the 4 quadrants. That means that we have the ability to do trig at angles that are bigger than 180. We can do trig at any angle we want, actually, both positive and negative. Yes, sir, you have a question. What's up? Well, like triangles that don't follow Euclidean geometry do have their own trigonometries, but we don't cover that in this one. So what we're doing is we're assuming flat universe here, so triangles that have to add up to 180. Alrighty, so first thing we're going to talk about is what does it mean for two angles to be coterminal? Co means together and terminal means end. So what we're talking about is two different angle measures that actually land in the same place in our quadrants. So two angles in standard position, which means their initial side is the positive x-axis, and terminal side, so if they have the same initial side and the same terminal side, but they have different measurements, we would call those coterminal angles. And we could pull that off with over-rotating or under-rotating, so to speak. I mean, if I were to jump and turn a circle, which I used to do before my back was really hurt, and land in the exact same position, if your eyes were closed when I did that maneuver, and then you open them again, you wouldn't know I moved at all. So adding 360 or 2 pi to an angle is essentially doing nothing because you land in the exact same spot. And not only is that true for adding, it's also true for subtracting. But that's not the only way that we can get coterminal angles. We can also get coterminal angles by opening the wrong direction but landing in the same spot as if we had opened the correct direction. So we're going to use our Greek letters other than theta. Alpha and beta is what it's showing you. Positive angles open clockwise, which we've already talked about. Negative angles, like what's being represented with beta over there, open clockwise. So I could have given us a negative angle for beta that is in exactly the same position as this positive red angle. I don't know, what do you want to say that's like 100 and the red one? Maybe like 170 degrees? So we could say that's around 170 degrees if we wanted to. It's an estimation. But if it's 170 degrees counterclockwise, and we want to land in the same spot going clockwise, we have to go the whole half circle right here. So there's your 180 plus this extra 10. So this would be negative 190 degrees. Those two angles are actually the exact same angle. They are coterminal because they end in the same spot. Now these two images, what I just described is in the bottom right, but this one in the bottom left is showing two positive angles that are coterminal simply by rotating one full circle, so 2 pi or 360 degrees, which is what I described when I said jump and turn, which I used to do back when I was young. But yeah, I don't know, angle alpha, is acute, right? It's less than 90. I could have said angle alpha is 60 degrees, or I don't know, how about we use radians for that one? We could say alpha is pi over 3. Then beta, which didn't stop when it hit the terminal side originally, went all the way around and hit it a second time, it would have been the pi over 3 plus another full circle. But those two angles are the same angle. Those ideas making sense? Because turning a full circle is essentially doing nothing. Because you land in the same spot. So for these examples, we've been asked to find and draw positive and negative angles that are coterminal with the one that we were given. So positive and negative. Well, positive is easy. You just add 360 degrees to something. Negative is actually pretty darn easy too. You just subtract 360. A full circle. So let's draw it, that way we can all see it. We're going to draw our quadrants. We will be calling these, I guess the quadrants, quadrantals, I don't know what we want to call them right now. So we're going to draw our quadrants, and we know that our angle has to be in standard position, so beginning at the positive x-axis and opening, picture not drawn to scale, out to here. So there's our 30-degree angle. If we wanted to get a positive angle that we can call alpha, then we need to land in the exact same spot, and the only way it's going to be positive is if we go one more full circle. So let's see, what color is good? This pink color feels good. So alpha doesn't stop at 30, it goes all the way around again, and then does that, landing at the exact same spot. So we can say alpha is 30 degrees plus 360 degrees, so 390 degrees. The angle 390 degrees and the angle 30 degrees are in the exact same position. They are coterminal. I'm sorry? Because it says to find a positive angle that is coterminal to the 30-degree angle. I mean, 30 is positive, yeah, but we needed to find another positive angle that was in the exact same position. Let's see, another color, what's going to work well here? Orange. Orange feels good. Beta will open clockwise, so it's going to go the wrong way, and it's going to land there. So there's two ways of thinking about this. You could either say you started at 0 and you went 330 degrees in the wrong way, so negative 330 degrees. Or you could say you started, so to speak, let's say you started here and then you chose to subtract 360 from that 30. Either way, you're going to land in the exact same spot. But technically, all angles in standard position begin on the x-axis, positive x-axis, and then either open clockwise or counterclockwise. The easiest way to do it, though, to think about it at least, is to say, oh, the 30-degree beginning minus 360, and that's how I'll write it. It looks like the orange thing, but the math that gets you there is 30 degrees minus 360 degrees. So 30 degrees, 390 degrees, negative 330 degrees, they're all in the exact same position in quadrant 1. Does it make sense? Yes? No? Maybe so? It's okay. All right. I don't like working in degrees, but we got another one here in degrees, negative 150 degrees. So let's go ahead and draw that. We draw our quadrants. It says negative, so this one's going to be opening clockwise, the wrong way. Draw it in blue. Negative 150. Well, that's more than 90, right? But it's less than 180. So that makes me land somewhere in quadrant 3. Picture not drawn to scale. And what I'll do is I'll say it opened like this. Negative 150 degrees. Okay. The positive angle that is coterminal to negative 150 degrees, again, remember, technically all angles are going to start at the positive x-axis, would have looked like this. That's what it looks like. Clearly you can see it's more than 180. How much more than 180 is that? It is 30 more. So that's 210 degrees. But if you're struggling to see why it was 210 degrees, you could have thought about beginning here and then turning a positive full circle. Either way, you're going to get the 210 degrees. So yeah, it would be great if you started seeing where things are landing in your mind in, well, preferably radians, but degrees, yes. But you know what's even more important to me is that you recognize that this angle, and I'm going to erase that in just a second, that I just highlighted over, that is a 30-degree angle. That's important because that's one of our special angles. All right, let's get our negative coterminal angle. Well, the green one, negative 150, was already negative, right? So the only way we're going to get another negative angle that's coterminal to the same spot is if we open to the blue one and then keep going and then do that. Looks like a snail shell. Essentially just saying, well, I already had negative 150 and I needed to subtract another 360, another full circle. What is that, 510? Yeah, negative 510 degrees. They're called circular functions because they repeat themselves every circle. Yeah, what's up? Looked like you had a question. Your hand went halfway up and then stopped. Oh, stretches like that. Okay, Karate Kid. All right. Yes, sir.
I don't really understand, why is that green thing?
The green one is the is the original angle. Okay, so the blue ray, that's funny, didn't mean it, the blue ray. The blue ray is the terminal side of the angle. So what I'm trying to show you is that you have this angle starting on the positive x-axis and then opening clockwise. So the green arrow is showing you the way that it opened. Because without that, you don't know if that was a positive angle or a negative angle. I didn't want to draw the green arrow in blue because I felt like that would have been confusing. So I drew it in green to show you that this was just me demonstrating how this angle was opening. So again, that angle's in standard position because its initial side is on the positive x-axis. It opened clockwise, which means showing you with the green arrow, 150 degrees clockwise. That means negative 150 degrees. Is that okay? So anything that's straight is a piece of the angle. The, the curly things is just me showing you rotation. It's motion.
How's the one on the top, the pink one,
How
how's it 210?
is it 210? Well, because if we had gone from here to here is 90 plus another 90 is 180, and then there's the other 30. So 180 plus 30 is 210. If you want to think about it, this negative 150, you could have thought of that as being 150 degrees less than a full circle. Full circle is 360 degrees, right? So we could have said that the pink one was 360 degrees minus 150 degrees to get us to 210. Is that okay? Cool. All right. Finally, radians. Remember, we don't always have to say rads or radians. It's assumed radians if you don't see a degree symbol. So what we're going to do is we're going to start thinking of pies as units. They're not units, but I think that helps people think about it. 2/3 of a pie. This is less than a full pie, right? Okay. Well, 0 is here, radians. Pi radians is here because, there's 2 pi radians in a full circle. 2/3 is 0.6 repeating, right? It's more than half. So up here would have been pi over 2. We have to go past the pi over 2, but we can't go all the way to the pi. Picture not drawn to scale. I'll even draw the terminal side, or the initial side. It's going to land somewhere in quadrant 2. Picture not drawn to scale, obviously. And we opened 2 pi over 3 radians, counterclockwise. Okay. Well, if we want another positive angle, but land in the same spot, all you could do is add another full circle to it. Yes, sir. It is 120 degrees, but I want you thinking in radians, not degrees. I'm telling you, the faster you can see the radians, the faster you're going to like trig. It's just, as far as I'm concerned, the radians just make life so much easier because the numbers stay small. If you said, real quick, where's 390 degrees? I'd be like, what? But if you said, oh, you're going to be, a pi over 6 past 2 pi, I'd be like, oh, okay, I know exactly where that is. It's just faster, I think, because people don't have multiples of 360 memorized usually. But multiples of 2, yeah, I got that memorized, The numbers are just so much smaller, they're easier to work with. So if we want a positive angle, the only thing we could do is go past where the grade 1 went, wrap all the way around, and hit the same spot again. So our alpha here will be 2 pi over 3 plus a full circle. Now, a full circle is 2 pi. But we're not going to say 2 and 2/3 pi because mixed numbers are awful. What we would do is we would convert that 2 pi into thirds. So that would be 6 pi over 3. You need a common denominator to add fractions. There, 8 pi over 3. See, I know where 8 pi over 3 is. I know that it's 2 more than 6 pi over 3. So it lands me in quadrant 2. Or you could think about it as 3 pi, which, by the way, this is coterminal to 3 pi right here. 3 pi would have been 9 pi over 3. So I'm clearly a pi over 3 before 3 pi. I've seen a lot of blank looks. Are we comfortable with why pi and 3 pi are coterminal? Because it's pi plus 2 pi. What? I said that this negative x-axis, if you want to think about it that way, that's pi radians. It's also 3 pi radians, 5 pi radians, 7 pi radians. See, I'm just adding 2 pi each time. No, degrees. Would what be 240? No, it's 120. Because pi over 3 is 180 divided by 3 is 60. And 60 times 2 is 120. Okay. All right. Then let's get our beta, our negative 1. Because that's what the directions say. We want a positive and negative coterminal angle to the one that was given. It's negative because it's opening clockwise. Angles are supposed to open counterclockwise. If you go clockwise, that's a negative angle by definition. If it moves in the same way that the clock's hands move, that's a negative angle. Okay? I'm just letting beta be negative. I could have chosen any letter I wanted. I'm just trying to have continuity as I go through the examples. The easiest way to find beta is to say your 2 pi over 3 minus 2 pi. Or minus 6 pi over 3. So it's going to give you negative 4 pi over 3. And remember, you don't have to say radians. If you don't have a degree symbol, it's assumed radians. What do we think about finding coterminal angles? No? Well, what can I help you with? While you're formulating your question. So 2 pi is a full circle. Okay. So yeah, so what I'm doing is I'm allowing it to turn a full circle either positive or negative, because if you turn a full circle, you should land in the exact same spot. But we want to be thinking radians, not degrees. So that's why we're adding and subtracting 2 pi. Why are they wrapping around a bunch of times? Do you mean, all right, which one? The pink one? All right, watch this. Come on. Oh, it's moving the whole image. How about that? I'll use my mouse for that then. Where is it? Where did my mouse just go? There it is. Okay. Let's see. This is a grouped image for some reason. How do I ungroup it? That's not working. Why is it doing that? Trying to ungroup it. Ooh, there's a lot of grouping here. Ha! Okay. You ready? I'm going to start at 0 radians. Am I pink? Pink. Okay, I'm going to start at 0 radians. If I stop here, I've gone 2 pi over 3 radians. But I already knew I was at 2 pi over 3 radians. That's what's in green. I was told I need another positive angle that's in the exact same place. So imagine you walked along that pink trip. You stopped where green stopped, and green was like, yo, 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 I was already here. You got to find another answer. The only way that you can land in the exact same spot is if you went around the whole circle again, like that. No, because the orange one was a negative angle. Remember, the pink one is what we're starting with. The green one's what we're starting with. We started with 2 pi over 3. The pink snail shell looking thing was the next positive angle that lands in the exact same spot. The orange arrow is me showing you the first negative angle that lands in the exact same spot. But it's not the only one. I could keep subtracting 2 pi an infinite number of times, and I'll land in the exact same spot that orange did. Or I could keep adding 2 pi an infinite number of times, and I will keep landing in the exact same spot that the pink one did. That doesn't matter. Adding and subtracting 2 pi lands you in the same spot. Okay? Yeah.
Wait, where's the 3 pi's just subtracting?
Well, I'm adding. Yeah. It's also negative pi, because you can say pi minus 2 pi. Yeah, that's the thing, is we don't want to think about, like, oh, that has to be 0 radians to the far right. No, that's 0. It's also 2 pi. It's also 4 pi, 6 pi, 8 pi, 10 pi. It's also negative 2 pi, negative 4 pi, negative 6 pi. Well, the one on the right, where it's 0, you could add 2 to it. So 2, 4, 6, 8, 10, 12. But the one on the left is a single pi, but you're still adding 2 to it. So 1, 3, 5, 7, 9. I mean, at the top, pi over 2. I could also add 2 pi to that. It's like 2, 2.5, like 5 pi over 2, 9 pi over 2. Okay. And the same thing with happening down here. Down there's 3 pi over 2. Okay, but so we'll get there. We'll get there, okay? More questions on that before we turn the page?
Yeah. Why do you subtract the orange one on the last one? Why you subtracted 2 pi? Like, I just don't get why you subtracted it.
Because I needed a negative number. That's why I subtracted 2 pi.
All right.
Here's the thing. The arrow, if you're watching just the arrow, from here to here, stopping right there, that would have been negative pi, right? Because it landed a half a circle away, but it's negative because I went clockwise. Then there was a little bit more. A little bit more. How much more? A pi over 3. And I know that because this is a pi over 3 away from 1 full pi, right? Because 1/3 plus 2/3 is 1. So that last little orange arrow that I drew right there, that one, that was a lot. This little arrow right here has a size of pi over 3. But because I'm going clockwise, it's negative. So I have negative pi and another negative pi over 3. Here's negative pi. Here's negative pi over 3. And pi is 3 pi over 3. So you could say this is negative 3 pi over 3 and negative pi over 3. The result is negative 4 pi over 3. But the easy way to get that answer, rather than all that hard work that I just showed, was to just take the positive number that you already knew and subtract 2 pi. Just turn a circle backwards so you land in the same spot. Okay? All right. That has got the crap explained out of it. All right, so let me clear this page. And let's move to the next one. What we got going on back here? Evaluating trig functions determined by a point in quadrant 1. It says let theta be an acute angle. The moment you hear that theta is an acute angle, that forces you in to quadrant 1. Acute means less than 90, and pi over 2 is 90 degrees, so now we're in quadrant 1. So theta is an acute angle, quadrant 1, standard position, terminal side has the point 5, 3 on it. Let's draw that. Picture not drawn to scale. What just happened here? There we go. I might have written too fast for the computer. There. We're in quadrant 1. Here's theta. Standard position. Standard position. And we have 5, 3 on the terminal side of our angle. It says to find the 6 trig functions of theta. Okay, well, I'll just drop an altitude. And yeah, that's a 90-degree angle because I said so. There. We have a right triangle. On the x-axis, the positive x-axis, what is the length of that horizontal leg? 5. Yeah, it's 5. Of course it is. Because that's the coordinate, 5, 3. So what is its y component? 3. So the green leg has a length of 3. All right. Well, trig is going to require me to know the hypotenuse, at least for a few of them. Tangent and cotangent could just use the 5 and the 3, but the other 4 are going to need that hypotenuse. How do I find it? What's the, thank you, Pythagorean theorem. Got to use that academic vocabulary. So we're going to find the length of our hypotenuse by using the Pythagorean theorem. 3 squared plus 5 squared equals, I'll say C. So 9 plus 25 is C squared. C squared is 34. And C, therefore, must be square root of 34. No perfect squares go into that, so we'll just say the square root of 34. Mr. M, isn't that supposed to be positive or negative? Well, no. And here's why. The hypotenuse of triangles, when they're graphed like this in our quadrants, always represent a distance. Hypotenuse of a triangle always represents a distance in trigonometry. It's the distance between our point and the origin. And distances are always positive. Okay? So the hypotenuse must always be positive. Now, we've all graphed points before. We're all well aware that x and y could both be negative. That's okay. But the hypotenuse cannot be negative. The hypotenuse represents a distance between a point and the origin. Okay? So, square root 34. Let's go. Sine of theta, which is going to be opposite over hypotenuse. You know, for now, we'll continue to use our safety blanket here. Opposite over hypotenuse will be 3 over root 34. If you know sine, you know its reciprocal cosecant. Let's flip it over. Get skinny, math. There. Cosine, AH for now. Adjacent over hypotenuse. You'll see what I mean by that. Cosine is 5 over root 34. If you know cosine, you know it's reciprocal of secant. And then the last two, the two that didn't require the hypotenuse. Tangent. What color have I not used yet? I used a lot of orange. Red. How about red? I haven't used much red. Tangent. For now, we'll say opposite over adjacent. So 3 over 5. And if you know tangent, you know it's reciprocal cotangent. 5 over 3. It's not too bad in quadrant 1, is it? Not too bad. Questions, comments, concerns on this question? Okay. So we're going to be able to get through this next question, and that'll be the end of it. But I suspect there's going to be questions. Now that one was easy because it was in quadrant 1. But what if you're not in quadrant 1? What if you're not in quadrant 1? Here we go. This time the point is -5, 3. Here's the nice thing. We already know the length of the hypotenuse. We don't need to do the Pythagorean theorem again. It's still 5 and 3. So that hypotenuse still is the same length, root 34. But this coordinate is in quadrant 2. Remember, all angles begin on the positive x-axis. Picture not drawn to scale. That is the point -5, 3. Here's the thing. Again, here we go. Always drop your altitudes to the x-axis, never the y-axis. I'm dreading this. Here you go. This is theta. Theta is not in the triangle. However, we will do the trig as if we are in the triangle from right here. This little spot right here that I'm putting dots on is called the reference angle. And that's why I was using that word a bunch when we were working on that worksheet. So theta, again, is outside of the triangle. Theta is obtuse. But we will reference this angle right here when we're doing our trigonometry. What number goes on the x-axis in this triangle over here? -5. Remember, this is not a distance. This is an actual coordinate. -5, 3. The only one of these things that's a distance is the hypotenuse. So this is still a 3, and the hypotenuse is still a root 34. But I'm hoping you could see any one of the trig functions that uses x is now going to be negative. Yes, they do. The adjacent side is x. Sine of theta, for now I'll let you say opposite over hypotenuse. But when we say opposite, we mean opposite of the red dot, because that's the reference angle. That's the angle we're referencing when we're talking about our trig. So it's going to be 3 over root 34. And then obviously the reciprocal of sine, cosecant, would just be the same fraction flipped over. How interesting. How interesting that two different coordinates, one in quadrant 1, one in quadrant 2, gave us the exact same sine and cosecant values that we had before. So interesting. Not yet, you don't. Now cosine of theta, adjacent over hypotenuse, this time our adjacent side, remember, meaning adjacent to our reference angle, the red dot, is negative. Negative 5 over root 34. So its reciprocal secant is also negative. How interesting. Well, what's the difference between saying the 5 is negative or the whole fraction is negative? There is no difference is the answer. As long as you know that a hypotenuse cannot be negative, you know which part of it's negative. But how interesting that cosine and secant gave us the exact same fraction in quadrant 2 as they did in quadrant 1, except for this time they were negative. How interesting. And lastly, tangent and its reciprocal. Tangent theta, which for now we'll say opposite over adjacent. When we say that, we're referencing the red dot. Opposite from the red dot is 3, adjacent to it's negative 5, so this is negative 3/5. And it looks like an S. Yuck. Try again. There we go. That's not much better. Whatever. Good Lord, it's only getting worse. And if you know tangent, you know cotangent. Just flip it over. So, how interesting that tangent and cotangent gave me the exact same fractions that they gave me in quadrant 1 and quadrant 2, except for the sign changed. How interesting. And what we've done can be extended to any quadrant. I could put that point 5, 3, I could have put it in quadrant 3 so that it was negative 5, negative 3. Then both the opposite and adjacent sides would have been negative. I could have put it in quadrant 4, 5 comma negative 3. Now only the opposite side would have been negative. So what this means is we can do trig at any size angle we want, not just angles that can exist inside a triangle. Yes, ma'am? No. I did not use a right angle as a reference angle. No, I used theta as my reference angle. I was just drawing that it's a right triangle. The theta always begins at the positive x-axis. Always. But the triangle could be in any quadrant. We reference the angle that's in the triangle when we do our trigonometry. And that's why I've been calling them reference angles. All right, we'll continue this on Monday.